coin-sized, but incredibly powerful. This thing could capture, well, every single electromagnetic frequency around us, from the low hum of the power grid all the way to Wi-Fi signals, radio waves, even sunlight, and then, just like that, turn it into usable power. It really sounds like something straight out of science fiction, doesn't it?
Yeah.
Okay, so let's unpack this. It's a really fascinating idea. For this deep dive, we're going to really examine the feasibility, Is this universal electromagnetic energy harvester even possible? We'll put it up against the fundamental laws of physics, the hard realities, our mission today. Cut through the speculation, however cool it sounds, and get to what's actually possible. And maybe more importantly, why some things just aren't.
Right. And what's really interesting here is how quickly this seemingly simple concept bumps up against some really core principles. We're talking electromagnetism, thermodynamics, the big ones. We'll look at the specific roadblocks, the independent barriers that pop up when you try to design something that, well, claims to do everything.
Okay, so where does this dream device first hit a snag? The antenna seems like the obvious place to start, right? How does something meant to pick up everything actually work? Or not work?
Well, exactly. The antenna is the first major hurdle. At its heart, antenna theory revolves around resonance. You should think of an antenna less like just a piece of metal and more like a tuned circuit, like a musical tuning fork, It only really vibrates well at its specific pitch.
We're like timing your push on a swing just right.
Precisely. Same idea. Electrically, this means an antenna's physical size, especially its length, has to correspond quite precisely to a fraction of the wavelength it's trying to receive. So, for example, a half-wave dipole antenna for the 40-meter amateur radio band, that's around 7 megahertz. It needs to be about 65.5 feet long.
Wow, that's big.
It is. But then the antenna for your FM radio, say at 105 megahertz, that's only about 4.4 feet long. See the difference? It's directly tied to the frequency.
Okay, so if one size antenna is really only good for one specific frequency range, then to capture all frequencies, from super low to incredibly high, you'd basically need an antenna that's somehow every possible size at once. That sounds physically impossible, isn't it?
It is, yes.
Yep.
That's a clear physical impossibility. And this isn't just a gut feeling. It's quantified by something called the Chu-Harrington limit. It's a fundamental theorem, really fundamental, that sets an absolute limit on an antenna's performance based purely on its physical size. It boils down to a trade-off, size versus bandwidth. How wide a range of frequencies can it handle? It relates to the antenna's Q factor, which, simply put, measures how sharp its resonance is. High Q means very sharp, very selective, very narrow bandwidth.
Okay.
And here's the key part for our omni-frequency idea. The smaller you try to make an antenna, especially relative to the wavelength it's receiving, or if you try to make one small antenna cover a huge range, including very long wavelengths, its minimum possible Q factor shoots way up, which means its maximum possible bandwidth shrinks dramatically, becoming almost infinitesimally small.
So trying to make it tiny and universal actually forces it to be extremely specialized and narrow.
Exactly. The two goals are fundamentally at odds. You're trying to make it microscopically designed, but that very act forces it away from being broadband, let alone omni-frequency. They are mutually exclusive.
But engineers are clever. They always find ways to push limits. What about things like fractal antennas? I've heard they can handle multiple frequencies. Could that be a path forward?
That's a great point. We do have sophisticated engineering approaches. Things like frequency-independent antennas, log periodic, or spiral antennas are examples. And yes, fractal antennas. They use these self-similar geometric patterns. It's clever. It lets them pack many different electrical lengths into one compact shape, so they can resonate effectively at multiple distinct frequency bands. There's research showing designs covering, say, 7 different bands, GSM, Wi-Fi, 5G, things like that.
So broadband or multiband, but not omni-frequency.
Precisely. These are really sophisticated compromises. They extend the range, yes, but they aren't breaking that fundamental Chu limit. They are broadband or multiband, covering several useful ranges. But that's a universe away from omni-frequency, covering everything. And often you sacrifice peak efficiency on any one band to get that versatility across several bands.
Okay. Barrier number 1. The antenna itself is physically constrained. Got it. But let's play devil's advocate. Let's imagine, just for a second, we could somehow build this impossible antenna. The next question is, how much energy is actually out there to grab? Is the air just thick with usable power?
Right. That's the second major reality check. Even with a perfect antenna, what's available to harvest? Our environment is saturated with man-made radio frequency signals, or RF cell towers, Wi-Fi routers, TV, radio broadcasts. They're everywhere. But crucially, their purpose is sending information, not delivering power.
They're designed to be detected, not to, run a motor.
Exactly. They are whispers, not shouts, in terms of energy. And studies back this up consistently. The power density is incredibly low. One German study, for example, found the median power density from GSM cell towers in homes was only about 200 microwatts per square meter. That's tiny.
Microwatts. Wow.
Yeah. Other surveys find similar numbers, maybe ranging from, say, zero point 0.2 nanowatts per square centimeter up to perhaps 1 microwatt per square centimeter in dense areas. Harvesting this is, well, it's like trying to fill a swimming pool with a very fine mist.
So not going to charge my phone anytime soon just by standing near a router.
Not even close.
Yeah.
It's just functionally negligible for most power needs.
Okay, so if the man-made stuff is basically an energy desert, what is the most genuinely widespread, truly ubiquitous electromagnetic energy source around us?
That would definitely be thermal radiation, sometimes called black body radiation. Basically, any object that isn't at absolute zero temperature. So everything around us is constantly radiating electromagnetic energy just because it's warm.
Just ambient heat radiating away.
Yes. An object at room temperature, for instance, radiates most strongly in the mid-infrared part of the spectrum. This is the energy source that's truly everywhere, all the time.
How does that compare power-wise to the Wi-Fi signal?
Oh, it's not even close. Let me give you some context. Direct sunlight, which is also electromagnetic radiation, has a power density about 10 million times greater than the average RF background in a city.
10 million.
Yes. And even just the Earth itself, radiating heat out into the cold of space. That thermal radiation represents orders of magnitude more potential power than all the ambient RF signals combined. This huge difference really reframes the whole problem. Even if you had a 100% efficient Omni-Frequency harvester, the amount of power you'd get from the RF environment would be practically useless for almost anything. The real energy isn't where we often think it is.
Okay, that's sobering. So hurdle 1, impossible antenna. Hurdle 2, hardly any power in the RF spectrum anyway. But let's keep pretending. Assume we grab all frequencies and somehow there's enough power. There's still another step, right? Converting it, turning that captured wave energy into usable electricity, like DC power. What's the issue there?
Yes, the conversion step. This brings up the third major barrier. Rectification. Can a single device actually take all these wildly different frequencies from kilohertz to petahertz, which is light, and turn them into useful DC power? The whole system, antenna plus rectifier, is often called a rectenna, and the rectifier is key.
And that's usually a diode, right?
Primarily, yes. Diodes are the workhorses for converting AC to DC. But, like antennas, they have their limits. Every diode has physical limitations. Things like parasitic capacitance, reverse recovery time.
Yeah.
Basically, internal factors that limit how fast it can switch on and off.
Electrical sluggishness.
That's a good way to put it. At very high frequencies, the diode just can't keep up. It stops rectifying efficiently. Instead of converting AC to DC, it just starts acting like a resistor, basically wasting the energy as heat.
So different diodes for different speeds.
Exactly. A standard rectifier diode, like a 1N4007 you might find in a power supply, works fine for mains frequencies, 50 or 60 hertz, maybe up to a few kilohertz, but it becomes useless pretty quickly above that.
Yeah.
Now, we have specialized diodes like Schottky diodes that can work well into the gigahertz range that covers microwaves, Wi-Fi, cellular.
Okay.
But when you get to terahertz frequencies like far infrared or hundreds of terahertz for near infrared and visible light, conventional diodes just can't operate. It's far, far beyond their switching speed capability.
Which brings up a point. We do harvest light energy, right? Solar panels. How do they work if diodes can't handle light frequencies?
Excellent question. Solar panels, or photovoltaics, PV, work on a completely different principle. They don't treat light as a wave to be rectified in the traditional sense. They work on a quantum level. Photons, particles of light, hit a semiconductor material and excite electrons, creating a current.
So it's particle physics, not wave rectification.
Precisely. And their efficiency is governed by different physics too, mainly the material's band gap. This leads to the Shockley-Queisser limit, another fundamental limit. For a standard silicon solar cell, that theoretical maximum efficiency is around 33%. Very effective, but it's not rectification.
Is anyone trying to actually rectify light as a wave?
Yes, there's research into what are called optical rectennas, or sometimes nanoantennas. These do try to treat light as an electromagnetic wave. A tiny nanoantenna captures the light wave, inducing an incredibly high-frequency current, and then they need an ultrafast diode to rectify it.
What kind of diode works at light speed?
Well, not conventional ones. They need exotic devices, often based on quantum tunneling, like metal insulator metal or MIM diodes. Theoretically, these optical rectennas aren't bound by the Shockley-Queisser limit and could, in principle, approach 100% efficiency. It's a fascinating area.
But the key point for our universal harvester.
Is that the technology needed to rectify radio waves and microwaves is fundamentally different, physically incompatible with the technology needed to rectify light waves. You can't just make one diode do both. It's different physics, different devices. So another nail in the coffin for the single universal device idea.
Okay, this is quite a list of impossibilities already. Antenna limits, low power density, rectification limits across the spectrum. But you mentioned there was one more barrier, something even more fundamental.
Yes. The final, and arguably the most absolute, prohibition, it comes from thermodynamics, specifically the second law of thermodynamics.
Ah, the big one, entropy and all that.
Indeed. In simple terms relevant here, the second law tells us you can't just extract useful energy or work from something that's all at the same temperature. To get work from heat, you need a temperature difference. An engine needs a hot source and a cold sink. It takes heat from the hot place, converts some into work, and must dump the rest into the cold place. No temperature difference, no network, period.
The universe's no free lunch rule, basically.
That's a perfect way to put it.
Yeah.
So think about our hypothetical universal harvester sitting in a room or just out in the environment. Eventually, it's going to reach the same temperature as its surroundings. Thermal equilibrium. At that point, it's absorbing thermal radiation from the environment, yes, but it's also emitting its own thermal radiation at the exact same rate.
Because it's also an object with temperature.
Exactly. So the net energy flow becomes zero. It's just part of the thermal bath.
And what does that mean for its ability to generate power?
It means it can't generate any net power. A passive device sitting in an environment at a uniform temperature has no temperature difference to exploit. Trying to build a device that passively sucks net energy out of a single temperature environment is effectively trying to build a perpetual motion machine of the second kind.
Which physics says is impossible.
Fundamentally impossible. This isn't an engineering challenge we can solve with cleverness or new materials. It's a hard no from the laws of nature themselves.
Whoa, okay, that feels definitive.
Huh.
So given all these barriers, antenna physics, energy density, rectification limits, and now thermodynamics, where does that leave things like, say, metamaterials? Could they offer some kind of loophole?
Metamaterials are really interesting, definitely. They're engineered structures, composites. They can have electromagnetic properties not usually found in nature. And yes, some metamaterials can be designed as near-perfect absorbers for specific frequencies. There are prototypes, for instance, showing really high absorption, like over 95%, and energy harvesting efficiency, but only at very specific microwave frequencies. Think 2.4 gigahertz or 5.8 gigahertz, Wi-Fi bands.
So, highly specialized again.
Exactly. Their unique abilities come from their structure, which creates specific resonances. So they are inherently narrowband. Metamaterials reinforce the point. They're about extreme specialization, making something work incredibly well for one specific frequency, not generalization to all frequencies.
Makes sense. And what about those more theoretical ideas that sometimes crop up about beating the Chu limit for antennas? Anything in there?
Yeah, people have explored concepts using active circuits or systems whose properties change over time. These can theoretically achieve wider bandwidths than the standard Chu limit suggests for simple passive antennas. But there's a catch, a fatal flaw for energy harvesting.
Let me guess. They need power.
You got it. They're not passive systems. They require an external power source to operate their active components or time-varying elements. They're designed to improve things like signal reception or transmission information transfer, not to produce a net surplus of energy. They consume power. They don't generate it.
So no free lunch there either.
Nope. Still bound by physics.
Really?
So connecting it all together, this deep dive really shows that while the dream of a single tiny device harvesting all electromagnetic energy is, frankly, really cool and imaginative, its actual realization is blocked, not just by one thing, but by a whole series of independent, insurmountable physical laws. You've got the antenna physics, the bandwidth limits.
The sheer lack of power in most ambient RF.
Right. Then the inability of one rectifier type to cover the whole spectrum.
And finally, the ultimate shutdown from the second law of thermodynamics.
It's really a cascade of no's.
But, okay, it's not all bad news, right? The idea, the ambition to harness this energy all around us, that's still valuable.
Absolutely. The spirit of the quest is completely valid and a powerful driver for real innovation. The takeaway isn't give up. It's just that the path forward isn't this single magic bullet device.
It's more about targeted solutions.
Exactly. The future lies in developing a whole ecosystem of different specialized technologies. For really low power stuff, like sensors for the Internet of Things, we'll definitely see smarter, more efficient multi-band RF antennas. Maybe using those fractal designs we talked about, optimized for the specific bands where there is some ambient energy or where energy is being deliberately beamed. For higher power needs, well, electromagnetic harvesting mostly means improving solar cells, or perhaps finding ways to efficiently harness waste heat using thermoelectric devices, exploiting existing temperature gradients. And those optical rectennas, the nantennas, they remain a really interesting frontier, high risk, potentially high reward. If they can be made practical, they could theoretically beat solar cell efficiencies for converting light to electricity. But again, specialized for light frequencies.
So the dream of the universal harvester might be impossible, but the push leads to real progress in specific areas. It forces us to be smarter, more targeted, not one size fits all.
Precisely. It's about understanding the limits and then innovating cleverly within those boundaries.
So thinking about all this, what stands out to you as maybe the most promising or just interesting direction for harnessing some slice of this electromagnetic world in a specialized way? Where do you see the focus going?